Okay, welcome to Let's Get to the Marks. Today I'm going through the GCSE Chemistry AQA Paper 2 2023. Let's smash those exams. Let's go. Question 1. A student investigated the rate of reaction between zinc and sulfuric acid. Hydrogen gas is produced during this reaction. Figure 1 shows the apparatus. We've got bubbles of hydrogen gas in the measuring cylinder. We've got the zinc granules in the conical flask here with the sulfuric acid. They added 50 centimeter cubed of sulfuric acid, 2 grams of zinc, quickly put the bung or the stopper in the top. And the first question says, suggest why the stopper must be put in the conical flask as quickly as possible. Pause the video, have a go, then I go through the answers. Okay, so why do we need to put the bung in the top of that flask as quick as possible? We're trying to measure the hydrogen gas that's bubbling up into that measuring cylinder through that delivery tube. If you don't get that bung in as soon as the acid and the zinc are reacting, then some of the hydrogen gas will escape and you won't get such an accurate recording of how much hydrogen gas has been produced. Now, it's impossible to get that bung in before some hydrogen gas has been released, because as soon as the acid touches the zinc, some reaction will take place and some hydrogen gas will escape. But the quicker you get the bung in, the less hydrogen gas will escape and the more accurate your measurement of hydrogen gas released will be. There we go. That's going to score you a mark, and that is for 1.1. So you can just write to reduce gas loss. Let's move on. 1.2, the student calculated the rate of reaction for each trial. Table 1 shows the results of the calculation. So we've got the rate of reaction on the left, and then we in the table, and then we have trial 1, 2, 3, and 4, and we have 4 sets of results. Determine the mean time taken to collect 20 centimeter cubed of gas. Do not include any anomalous results. That do not is key. That's going to score you a mark there. Use the equation. It's going to score you a mark if you use this equation as well. Mean rate of reaction is equal to volume of gas over mean time taken. This is a whopping 5 marker. So lots of easy marks to score here if we follow these parts of the question carefully. So the first thing is they want the mean time taken. That's circled there. So we need to rearrange the equation. So if you know your maths, you want to do volume of gas divided by the rate of reaction equals the mean time taken. And that's going to score you your first mark. Now, one of the things I've underlined in black there is do not include any anomalous results. And they've said we're obviously going to need to calculate the mean rate. So to calculate, but do not include the anomalous results. So we need to add up all these numbers, but can you spot one that's a bit out, is an anomaly, is an odd result? Well, 0.78, 0.81, they're pretty similar, and another 0.81, pretty similar, but 0.68 is quite a bit different. So this is known as an anomalous or an odd result, a result that doesn't fit the pattern. And we should not include this in our mean. If you do include it, you'll just drop 1 mark. They won't punish you for the rest of the marks in the question. So if you did accidentally include this, don't punch yourself in the face, but you get an extra mark for not including the anomalous result. And this is often a question actually on means. And so you've got to remember that. Always take the anomalous out. So we're going to go 0.78 plus 0.81 plus 0.81 divided by 3. And that is going to give us our mean rate of reaction. And then we need to find the mean time taken. So we're going to do volume of gas, which is 20, over 0.8, which is the mean rate of reaction. Now, you will score 1 mark for locating and taking the anomaly out of this, and 1 mark for working out the mean. So even if you didn't take the anomaly out, you'll still get a mark for working out the mean. Even though it's incorrect, you'll get error carried forward. So the final answer is 20 divided by 0.8. I'm getting rid of centimeter cube. We don't need that. They've given us the unit seconds, but just in case you wondered why it's seconds, you cancel out the 2 centimeter cubed. So 20 divided by 0.8 is 25 seconds. And that's going to get you your full fat 5 marks. Brilliant. Okay, make sure you hit the like, you subscribe and all that stuff. It really helps with my channel. Hope you're enjoying the video. 1.3, the student changed the investigation so that the mean time taken to collect 20 centimeter gas was greater. So they changed the investigation so it took a longer time to get 20 centimeters of gas. What 2 changes would increase the time taken to collect 20 centimeters of gas? Think about it. If it's taking a longer time to collect the gas, is the reaction happening faster or slower? the reaction must be happening slower. The acid and zinc are reacting slower. What two changes would you make here out of this list with the boxes next to them that would slow down the reaction? So would you use a catalyst? Does that slow down reactions? Would you use a larger conical flask? Would you use a lower temperature? Would you use smaller pieces of zinc? Would you use sulfuric acid at a lower concentration? Well, think about it, pause the video, have a go, unpause, check out the answers. Right, first of all, if you use a catalyst, that lowers the activation energy, so that would increase the rate of reaction. A larger conical flask won't do anything. Use a lower temperature. Yeah, that will be less kinetic energy, less chances of particles colliding. Smaller pieces of zinc, that will actually increase the surface area and the rate of reaction. So the final answer is to tick the final box, which is a lower concentration, which means less particles, less successful collisions. Boom, let's move on. 1.4, hydrogen gas is produced during this reaction. Describe the test for hydrogen gas. You should know these off by heart, including the oxygen and chlorine test. You also have to know those. With the hydrogen test, we place a lit splint by wherever the gas is coming out of, so by the opening to a test tube, a beaker, or a conical flask. Place the lit splint there, you're going to hear a squeaky pop, a squeaky pop sound. And you should know that off by heart. Nice, easy peasy 2 marks. Those tests, chemical analysis tests in chemistry, like the gas test, the flame test, they're really suited to revision card practice. I'd make revision cards to memorize all the tests because it's just content. There's no understanding needed. All right, let's move on. That is the end of question 1. I hope you did well. Let's get on to question 2. GCSE exams coming up. We've got to smash them. And the only way to do that is by practice, practice, practice. This question is about alcohols and carboxylic acids. Alcohols are used as fuels. In Brazil, they use alcohol in cars as fuels. A student burned 1 gram of alcohol and determined the energy released from each. So look, they've compared different alcohols. We've got ethanol, propanol, butanol, pentanol, hexanol, and heptanol. And we've got the amount of energy released from each one when 1 gram was burnt. Calculate the mass of ethanol that must be burned to release the same amount of energy as burning 1 gram of heptanol. So heptanol has 7 carbons. It's down here at the bottom. I'm circling it in pink. And it releases, when you burn 1 gram, it releases 39.8 kilojoules, or 39,800 joules, but 39.8 kilojoules of energy. If we look at ethanol, which is right at the top, I'm going to circle this in blue. This has only got 2 carbons, and it releases 29.6 kilojoules of energy when you burn a gram. So obviously we'll need to burn more ethanol to get the same amount of energy as hexanol. So all you've got to do here is take the amount of energy for heptanol, which is 39.8, divide it by 29.6, and you'll get how many grams of ethanol, how much more ethanol you need to burn to get the same amount of energy. So we're going to need to burn 1.34 grams of ethanol. So you need to burn 1.34 times as much ethanol because it doesn't release as much energy. And that will get you 2 marks. Boom. Okay, this next question is a graph question. And you're basically going to get a bunch of marks for just plotting the results. You don't even have to do a line of best fit for this one. So we've got the number of carbon atoms in the molecule, and you can see ethanol has 2. So, and it gives out 29.6. So we've got to find where's 29.6. If you do the maths on this scale, each small square is equal to 0.2. So that's where we want to put the first dot. And then we've got 3 carbons. We go to the third line there, 3 carbons for propanol and 33.6. So we're going to go 33 is in the middle, and then 0.6 is 3 little squares up because each one is 0.2. And then for 4 carbons, we've got 36.1, etc., etc. So we've got some lovely easy marks here just for basically putting on the different points, getting them within 1 baby square. You can make a mistake by like 1 little baby square out and they'll still give you the marks. And then also there is an 8th carbon which is not found on the table, and you can guess the next question is going to be, can you predict the number for the 8th carbon? So what we want to do here for the last one, because we got the table of results will give us up to 7. Just follow the pattern for the next one. So for the 8th one, I'm going to do it in another color just so you can see what I'm on about. That's not found in the table, but if you just follow the curve of that line, you'd say that's about right. Maybe a bit lower, actually, maybe like 40.4. Anyway, they will accept anything between like 40 and 40.8, something like that. So that's what they want us to do. So that's what we're going to do. We're just going to write down our prediction for when it's a 8 carbon molecule. And I reckon it's about 40.8. It's probably a little bit lower than that because it's starting to curve off. So it's probably a little bit lower. Maybe 40.4 would be better. But there we go. I'm going 40.8. Let's live dangerously. All right, let's move on. Carbon dioxide is produced when alcohols are burned. Carbon dioxide is identified by bubbling gas through lime water. Which of these is the true nature or chemical name for lime water? And it's calcium hydroxide. You just got to learn that off by heart. It actually forms calcium carbonate when it goes cloudy. And of course, the result of lime water when it touches carbon dioxide, it goes cloudy. And that's because it forms calcium carbonate, which is like chalk. Okay, 2.6, ethanoic acid can be produced from ethanol. What is reactive with ethanol to produce ethanoic acid? So if you think of alcohol, like wine or something like that, not that alcohol is always for drinking, you've got hand washes, solvents, and other uses of alcohols. Well, when oxygen gets to it, it's oxidized, it becomes vinegar, it becomes a carboxylic acid. Right, now for this next question, why don't you pause the video, have a go, write it on scrap paper, and then unpause. Okay, we just got to fill in the bonds here for the functional group of carboxylic acids. So we've got a double bond between the C and the O and a single bond between the C and the OH, because carboxylic acids have this, which is the carboxylic acid group. And R is the rest of the chain, if it's propanoic acid, butanoic acid, etc. Right, 2.8. Ethanoic acid reacts with different compounds. Draw one line from each compound to the product of the reaction with the compound with ethanoic acid. So pause the video, have a go. All right, so when you look at ethanol, when it reacts with ethanoic acid, ethanol and ethanoic acid, they make an ester. And the ester in this case would be ethyl ethanoate. In the AQA syllabus, you only need to name one ester, and that's ethyl ethanoate. And that is made from the alcohol ethanol and the carboxylic acid, ethanoic acid, and that gives us ethyl ethanoate. So the reaction between an alcohol and a carboxylic acid makes esters. Esters are great in perfumes and in the food industry because they've got lovely sweet smells. They're also pretty good solvents as well. Sodium carbonate, well, that is one of the tests that you're dealing with an acid. If you add sodium carbonate to ethanoic acid, it's going to release carbon dioxide, and you can do the lime water test. It will go cloudy, the lime water, and prove that you're dealing with an acid. You can add it to any acid. It doesn't just have to be carbon dioxide. There we go. How did you do? That's the end of that question. Next, we're going through question 3. Okay, let's get into question 3. It's our big old 6 marker. This question's about chemical analysis. Potassium bromide is used in medicine. A scientist tested a sample of medicine to show the presence of potassium ions and bromide ions. The sample is soluble in water. So here is the symbol for potassium bromide, KBr. Of course, when dissolved in water, it will split into its ions. So you actually do need to dissolve it in water. And you'll get potassium K plus ions and bromide ions Br minus. So if you have an aqueous solution of potassium bromide, you're going to be able to test it for the presence of these ions. So plan a method the scientists could use to show the sample of medicine contains potassium ions and bromide ions. And here are the following pieces of apparatus. So pause the video, have a go, and then unpause, write your answers on some scrap paper and then check it against the walkthrough. Okay, let's go. So first of all, although it's not on the mark scheme, you would want to dissolve the potassium bromide into the solution so that the ions are present and free to move about. Then, of course, we're going to want to do a flame test, and that will test you for the cations, the positive ions, the metal ions here. So you're going to clean the wire first, often with hydrochloric acid, burn it off through a Bunsen burner flame, or wash it with distilled water. All of those are descriptions of how to clean the metal wire. You don't want impurities from any previous tests confusing your flame test result. Now, you do need to dip the wire into the potassium bromide solution. The bromide ions don't give off a flame, but the potassium ions will. Now, we pass that flame through the non-luminous part of a Bunsen burner flame. Sorry, we passed the wire into a non-luminous part of a Bunsen burner flame. So I'm just going to quickly scribble out a little Bunsen burner drawing. Notice, to get the blue flame on a Bunsen burner, you have to open the hole on the Bunsen burner, and then you're going to get a blue flame. Now, the dark blue part you don't want to use because that can confuse your test, because copper ions and other things give off a blue flame, so that'll mess your test up. But there's a light blue part around the outside of the blue flame. We call this the non-luminous part, and it's there that you want to put your metal wire, which is coated in your potassium bromide solution. The non-luminous part will enable you to see any color changes, i.e. an orange flame, a green flame, a blue flame. It won't be masked by the luminous part, which is that bright orange blue bit right at the bottom of the flame. You don't want to use the luminous part because that will mask any color changes or for your flame. This is going to get you 3 marks. So what are the 3 marks for? The 3 marks are for cleaning the wire. So any description of cleaning the wire will get you a mark. Dipping the wire into the sample and putting in the non-luminous part of the flame is the 2nd mark. So using the non-luminous part of the flame. And the 3rd mark is for giving the correct color change for potassium ions, which of course is lilac, purple, or pink. Lilac's the preferred answer, but purple or pink are always accepted as well. And that will get you 3 marks. Now, the second part of the test, we've got a test for the anion, the negative ion in this solution, and that is the bromide ion, the Br- ion. So there's a specific set of chemical analysis tests. These lend themselves to revision cards brilliantly. Anywho, these are the halide ions, the halogens, once they've gained an electron. And the way to test for a halogen or a halide ion is to use nitric acid and silver nitrate solution. So that's going to get you a mark. You're going to use nitric acid and silver nitrate solution. And what's going to happen is you're going to get a different color precipitate depending on the ion. So bromide ions give us a cream precipitate, but above them in group 7, chloride ions give you a white precipitate, and below them iodide ions yellow. I call it the off milk test. It's like milk going off. So it goes from white with chloride ions. If you have bromide ions, it goes cream, and then iodide ions is like really off milk. It goes yellow. So that's my way of remembering it. I think of a glass of milk going off, going white to cream to yellow as you go down group 7. Fluoride ions do not give off a colored precipitate, or it would just be white or colorless. I don't think they give off a precipitate at all. Don't ask me why I've written bromide ion cream prep. That's supposed to say prep for precipitate. Anyway, that should gain you 6 marks. Let's move on. Keep moving on, keep moving on, keep moving on, keep moving on. The scientists could also use an instrumental method to show the presence of potassium ions in the medicine. Which instrumental method could be used to show the presence of potassium ions in the medicine? So this is a really accurate method of showing that there's potassium ions there rather than the flame test, and it's called flame emission spectroscopy. Give one advantage of using this instrumental method instead of a chemical test. Well, the main advantage of flame emission spectroscopy that you can't get with a flame test with a Bunsen burner is you can work out the concentration of the ions, because you will get different intensities in the flame emission spectroscopy. So you'll be able to work out the concentration of potassium ions as well, which you can't do with a flame test. It's more sensitive, it's more accurate. All of those are acceptable answers. All right, let's move on. How did you do? 8 out of 8, I hope. Okie dokie. Carbon dioxide and methane are greenhouse gases. This question is about greenhouse gases and climate change. Which of the following is also a greenhouse gas? Chlorine? No. Nitrogen? No. Oxygen? No. It's water vapor. Thankfully for the water, because of the water cycle, we're not getting a massive increase in water vapor in the atmosphere. Right, the next part says, in the past 50 years, there's been an increase in the world population, the concentration of CO2 in the atmosphere, the concentration of methane in the atmosphere, the mean temperature of the Earth's surface has increased. Most scientists think this is because of climate change. Explain why the increase in the world population may have caused the increase in concentration of carbon dioxide in the atmosphere. So why, because there's more people, will we get more CO2 in the atmosphere? There are load of answers for this, excuse my language. More transportation means more combustion of fossil fuels, more heating in the homes, greater population, more burning of fossil fuels to keep warm, more combustion, more CO2 release, more landfill sites for all your rubbish where it gets decomposed and that can release CO2 as well. We've got deforestation to clear the area for homes and houses. So less carbon dioxide locked up by photosynthesis. So an increase in greenhouse gases. Also clearing forests in order to make more farmland. We call the fancy name for that agriculture. So increasing need for crops for a growing population means we have to clear more forest to make um, so all of these are just some of the points of how humans are increasing the amount of carbon dioxide in the atmosphere. Okay, let's zing to the next part. Right, 4.3, explain why the increase in world population may have caused the increase in the concentration of methane. So methane comes from rice fields and from cattle, cows. So cow farts, basically, excretion from cows or cow waste. And of course, as there's more people, we're eating more cows, we're eating more rice, and both of those, the cattle and the rice, produce methane. So there we go. That is the explanation for why we're getting an increase in CO2 um, in the atmosphere. Sorry, not CO2, methane in the atmosphere. Of course, methane has the formula CH4, not CO2, that's carbon dioxide. Zing, zing, zing. 4.4. Describe two potential effects of the increase in the mean temperature of the atmosphere at the Earth's surface. So, again, there's a list of about 20 things here. If the atmosphere at the surface of the Earth, so where we live, if that is increasing in heat, what's that going to do? What are the effects? So, we've got melting the ice caps, more flooding, we've got sea levels rising, habitat destruction, species extinction, increasing temperatures in some countries. Think of the south of Spain, which is becoming like a desert, desertification. What the hell is that? Droughts, basically. Crops die, less food available, species extinction. We've already said that. There's literally hundreds and hundreds and hundreds of effects of global warming. Recently on the news, you've probably seen forest fires everywhere, especially in America, in Los Angeles. So we're going to get more forest fires, more destruction of homes, and more extinction of species and loss of habitat. Awesome. Right, and moving on to the last part, 4.5, the mean temperature of the atmosphere at the Earth's surface has increased. Most scientists think that this has been caused by an increase in the concentration of greenhouse gases in the atmosphere, but what's the reason why some scientists don't believe this? Well, very interestingly enough, the Earth has been a lot hotter than it is today, and has been a lot cooler than it is today. Quite simply, global climate changes throughout our history, and we have lots of scientific evidence for this from ice cores. I mean, we've found fossils from England, the UK, where it used to be very, very warm, and we found places which were deserts used to be very, very cold. So global temperatures change through activity from the sun and just other many, many, many complicated factors. Okay, we're into question 5. Let's go. Copper is extracted from metal ores. Chalcopyrite is a metal ore containing a compound with the formula CuFeS2. CuFeS2 reacts with oxygen to produce copper 2 sulfate and iron 2 sulfate. Complete the equation for the reaction. Zooming in, you should balance the equation. Now, you might be wondering what the little number in brackets means, the Roman numerals, so copper 2 and iron 2. This tells us that the metal ion in these ionic compounds, it tells us their positive charge. So, for instance, copper 2 sulfate has a 2 plus charge, and iron 2 sulfate has a 2 plus charge. So, iron 2 sulfate has Fe2 plus ions, and copper 2 sulfate has Cu2 plus ions involved. Helps you with working out the formula of compounds, but simple enough here, we don't have to do that. We simply have to write down oxygen because here it says it reacts with oxygen. It tells us what the reactant is. So we get 1 mark for that, for just putting O2 there in the equation. Now we need to balance it. Well, there's how many oxygens on the right-hand side? There's 4 there and 4 there. That's 8 in total. And we need 8 over here. So we're going to do 4 O2s because 4 times 2 equals 8. And there you go. That's your second mark. Bob's your uncle. Fanny's your aunt. Boom. Right. 5.2. Calculate the percentage by mass of copper in copper, iron, sulfur. Lovely. In this compound, whatever the hell that is. Um, so what we need to do here is work out how much copper is in the total. So what you're really looking at is dividing the mass of copper, which we've been given with these atomic masses, over the total mass, including the copper in the total mass, timesing it by 100 to get a percentage. So we want to really look at copper and say, well, copper is 63.5. So there's 63.5 over the top of 63.5 plus 56 plus 32 times 2. The 32 stands for the sulfur. That's the relative atomic mass of one sulfur, but we've got two sulfurs. So we need to multiply that by 2. Make sure you bracket everything in your calculator, otherwise you might come up with the wrong answer. For some people, it's easier to just break the sum down into little parts as well. And then we're going to times 100. So this is going to give us like 0.34, something like that. And then we're going to multiply by 100 to work out the actual percentage of copper within that molecule. And once we times 100, we get 34.6%. And that's your answer for 3 marks for 5.2. Let's zing to 5.3. Describe a test to show the presence of copper 2 ions in a solution of copper 2 sulfate. Give the result of the test. So the test for copper 2 ions, you can do a flame test. So dip some of the sample in the non-luminous part of the flame using a metal wire. You'll get a blue or a blue-green flame, or a green flame, you can say, for copper 2 ions. There's an alternative test where you react it with sodium hydroxide solution, hence the AQ in brackets here, and you get a precipitate formed, a blue precipitate. These are 2 separate tests, so you need to include one or the other, not both, and not a mixture of each. So flame test goes blue-green flame, or react with NaOH solution, you get blue precipitate. So either one will get you the 2 marks. Right, 5.4. Copper can be extracted from low-grade ores by bioleaching. Describe what is meant by bioleaching. Okay, so bioleaching is when bacteria live on a rock and they extract minerals for their own survival from the rock, and they create this into a solution which we call a leachate, and it comes out of their bodies, and we can use electrolysis or displacement reactions to extract it. Now, low-grade ores, these rocks, don't have a lot of metal ions in, so it's not economically viable to extract it via other methods like the blast furnace or electrolysis on its own. So we need the bacteria to do a lot of the work for us, and that makes it economically viable and kind of an environmentally more sustainable method of extracting metals. Cool. But your key marks here are to just say using bacteria, and they create a leachate. Right, let's move on to the next question. So we're now on to question 6. This question is about chromatography. A student investigated an orange food colouring using 2 different types of chromatography paper. The food colouring contained a mixture of red and yellow dyes. It was soluble in water. This is the method used. Draw a short line on a piece of type A chromatography paper. Put a spot of orange food colouring on the line. Put the paper into a beaker containing water as a solvent. Wait for the water to travel up the paper. Measure the distance above the start line moved by the red and yellow dyes and the water. Repeat steps 1 to 5 with chromatography paper B. Figure 3 shows how the apparatus was set up by the student. And our question here is 6.1. It says there's 2 mistakes made here. You should be able to spot them. When setting up the apparatus, give the 2 separate mistakes the student made. So first of all, you can see here they drew the start line in ink. That's a bad thing. Ink can dissolve in solvents and it can run, colour the water and smudge the paper and ruin your chromatography. It can climb up the paper and confuse what's going on with your dyes. So it's best to use a pencil. And the second mistake they used, the water or the solvent is above the start line. Once again, this means that, again, That's really poor because it means the dye, will already dissolve into the water and it won't climb up the paper because it will just dissolve into the solvent, the dye. So you'll end up with coloured water and you won't get that pattern on the paper that you're looking for with chromatography. All right, let's move on to the next part of the question. So 6.2, we've been given a table of results for type A chromatography paper and type B. So they used the red and the yellow dye on both different types of chromatography paper. We've got the distance moved by the dyes, and then below that we've got the distance moved by the water, which has moved 12 centimeters each time, and then we've got the RF value. Determine X in table 3. So they want us to determine how far the yellow dye moved with chromatography paper B. Well, there's an equation you need to know off by heart, and unlike physics, you don't get an equation sheet. So the RF value is the distance moved by the dye divided by the distance moved by the solvent. In this case, the solvent is water. We call this the solvent front, the end where the water gets to. So that's the distance, okay, moved by the water. So let's look at the first one here. We've got the distance moved by the red dye, 4.8, and the RF value is 0.4. Well, if you times 0.4 by 12, which is rearranging the equation to find the distance moved by the dye, you go RF value times the distance moved by the water, so 0.4 times 12, you get 4.8. So let's do the same thing here for the missing yellow dye. So we know the RF value is 0.6, so we want to times it, the RF value, by the distance moved by the water by 12, and we're going to get 7.2, and that's going to get you 3 marks. Beautiful. All right, let's move on to the next question because smashed out 3 marks there. Changing the type of chromatography paper resulted in different RF values for the red dye. Explain why the RF values for the red dye, I didn't even finish reading that question. So we're looking at the red dye here and we're comparing it with the 2 types of paper. Explain why it got a different RF value. See, it's got 4.8 with the first one and 5.4 with the next one. So this is worth 3 marks. Why did it have a different RF value in each? Well, the reason is that it had a different RF value is because in chromatography paper A, it had a lower RF value because it didn't travel as far. Remember, the RF value is the distance of the dye over the water. Well, it obviously didn't go as far in the first one as it did in the second one. It went like 4.8 centimeters in the first and 5.4 or 5.6 in the second. So on chromatography paper A, it had a lower RF value because it traveled a shorter distance, and that will get you 2 out of the 3 marks. Now, the explanation is the hardest mark. The third mark is, why did it travel a shorter distance? And the reason is that with chromatography paper A, the red dye had a greater attraction to the paper or the stationary phase, or we can say it was retained by the paper for a greater length of time than it was with chromatography paper B. So the idea is the red dye is more attracted to the stationary phase with A than it relative to its attraction with the stationary phase with B. And that's essentially the last mark. There's quite a few different ways you can word that. So here's an alternative way, which is just a little bit clearer. The RF value of the red dye on paper A is lower than on B because it spends more time retained on chromatography paper A than it does on chromatography paper B. So basically it's more attracted to paper A than it is to B, or the stationary phase A to stationary phase B, and therefore it travels a shorter distance up the paper because it's actually not spending as much time in the mobile phase, in the solvent, the water. See, what it's doing is flicking between the stationary phase being stuck to the paper, the dye is, and then being dissolved in the mobile phase, the solvent. And when it's dissolved in the mobile phase, it moves. And when it's stuck to the paper, it doesn't move. So essentially it has a greater attraction to paper A than it does to paper B. So it spends more time stuck to the paper and less time moving on chromatography paper A. Quite complex, I know. Right, 5.4, the last bit. What other change to the investigation could result in a different RF value? So of course, if you want to make the red dye or yellow dye move different distances, just change the solvent. You could use ethanol, a ketone like ethanone or propanone. There's no such thing as ethanone. You could use propanone or ethanol, and yeah, it will move different distances depending on its attraction to those solvents or its solubility in those solvents. All right, let's move on. Okay, getting into question 7. Here's 7.1. Explain how a manganese dioxide catalyst increases the rate of decomposition of hydrogen peroxide. And this one is worth 2 marks. It's basically asking you, what does a catalyst do? So catalysts can be used again and again. They're used a lot in industry to speed up chemical reactions. But the two things you need to know as a GCSE chemistry student on how a catalyst works, and when it says the word explain, you've got to give the science. A catalyst works by providing an alternative route for a reaction, which enables it to have a lower activation energy. So there you go. It makes an alternative route with a lower activation energy. And that's worth 2 marks. So you'll get 1 mark for saying provide an alternative route and another mark for saying lowers an activation energy. The next question, a student investigated the rate of this reaction. This is the method used. Add 50 centimeters of 2 mole per decimeter hydrogen peroxide solution to a conical flask. Add 1 gram of manganese dioxide to the conical flask. Place the conical flask on a balance and start the timer. Record the total mass lost from the conical flask every 20 seconds for 180 seconds. We need to explain here, why did the mass inside the flask go down? Why did it decrease? So during this reaction, a gas is produced, and gases have a mass, and of course, the gases can escape through the end of the conical flask. It should really have a bung in it or something in it to stop the gas escaping if you don't want it to escape. But the whole point of this reaction is we want the gas to escape, so the mass goes down, and we can time it and see how quickly the mass is lost and use that as a measurement of our rate of reaction. We're measuring the amount of time it takes to lose the mass. So mass per second that is lost. Anyway, so that's why it goes down, because gas has a mass and it's losing mass from the top of the conical flask. Now we have another question here. It says determine the rate of reaction when the time is 75 seconds. Give your answer to 2 significant figures. So let's go through how to do this. So a tangent line, a tangent to the line has been drawn at 75 seconds. So if you follow up where it says 75 seconds on the x-axis, I'm going to draw a wobbly line here in red and draw a little circle there. That's at 75 seconds. They've drawn a line like this. It's best to draw the line, if you're doing it yourself, to touch both axes and have equal amount of space below the line on each side between the curve and the line. That helps you with drawing tangents. Okay. So what do we have to do? They want us to determine the rate of reaction using the tangent line. Well, what we need to do is find the gradient, and we do that by doing y divided by x. Now, the y-axis is the vertical axis and x is the horizontal. So all you need to do here is divide y by x and give your answer to 2 significant figures. Y over x to 2 sig. So the difficulty, why this is 4 marks, is because each square on the y-axis and x-axis equals a different number. So if we look at the y-axis, there is 0.2 between each sort of 1 centimeter square on the graph. And then each baby little square, the smallest square on the graph, is therefore equal to 0.2 divided by 5, because there's 5 small squares between the measurements. So each small square on the y-axis is worth 0.04. Now, I've written that a bit bent, but you want to take the top measurement. So let's rub that out and write that again. You want to take the top measurement, which is 176, 1.76, I should say, not 176. Never mind. So it's 1.76, and we want to take away 1.24. So this means that y is equal to 0.52. Now we need to find out x, because we want to do y divided by x. So how do we work out x? So remember, first of all, for y, what I had to do is go, each one of these squares is worth 0.2, right? So I had to work out that each baby square on the y-axis is worth 0.04. Not 4, 0.04, because essentially you're doing 0.2 divided by 5. and you get 0.04. So what we have to do to work out x is first of all work out how much each little square is worth on the x-axis. And each little square here is worth, it looks like 25 divided by 5. So each little square is worth 5. And that is on the x-axis. So now we need to go to the top up here, and we need to measure the length of that line in little squares times 5. So x is equal to 125, and then we're going to minus 25, and that will give us our answer for x. I just zoomed in a little here so you can see it a little clearer. So x is 100. So now all we need to do is go 0.5 divided by 100, and then we need to round to two significant figures. So let's do that now. So y over x is 0.52 divided by 100. You get 5.2 times 10 to the minus 3, standard form, or you could write 0.0052, and that is to two significant figures. So the marks here, one for drawing the tangent, one for working out y, one for working out x, one for carrying out the calculation, and 2 sig. And there we go, 4 lovely marks. All right, let's move on to the next part of the question. Okay, moving on to 7.4. Figure 4 shows the results for 50 centimeter cubed of hydrogen peroxide solution and 1 gram of magnesium dioxide, shown again here on this figure 5. These results are 50 centimeter cubed of 2 mole per decimeter hydrogen peroxide solution. They're asking us and saying the student repeated it down here with only a 1 mole decimeter concentration. So what have they changed? They haven't changed the volume. That's still 50 centimeter cubed. They're still using 1 gram of manganese dioxide. What they've done is half the concentration, mole per decimeter. They want us to draw a new line for these results when they've halved the concentration. If you half the concentration, you half the number of particles. And this means you're going to have half the amount of product produced, because you've only got half the amount of atoms or particles or molecules to react. So our line needs to finish roughly halfway. And as this goes up to 1.6 on the y-axis, ours needs to finish at 0.8. And that will get us 1 mark. The other mark is also, because there's less particles, look at my curve, my pink curve. It's taking a longer time. It's not as steep. And this is because there's less particles, there's less probability of a successful collision, so we have a lower rate of reaction. So it takes longer for the reaction to finish, longer until that line straightens, and also there's only half as much gas or product produced. So the lossing mass is happening slower, and we only get half the total mass loss. All right, let's move on. This question is about polymers. We've got chloroethene can be used to produce an addition polymer called polychloroethene. The display structural formula of chloroethene is here. Draw a circle around the functional group that allows it to become an additional polymer. And the key here in this monomer is that it has a double bond. And monomers are unsaturated. Often alkenes are unsaturated as well and have double bonds. And that means they can undergo addition reactions by opening up. Now, the next part to this question, 8.2, wants us to complete the diagram to show the polymer. So when you're given the monomer, and the monomer of an addition monomer will always have a double bond in the middle. Two things when we're drawing the addition polymer. Polymer is when you stick lots of monomers together. Two things we need to do. Number one, draw lines, 2 lines going horizontally outside of the brackets. And number two, you need to remove the double bond in the middle and replace it with a single bond. Everything else you keep the same. So all the H's and Cl's you keep the same. So look, there's my first mark. I've put a single bond here. Now I keep the H's, the Cl the same in the exact same place. And then this first point here, draw the bonds going outside the brackets. Now I need to draw a line coming out, going into outside the brackets on each side, and don't put any letters or elements on the end of those lines. You need to leave it open. And the final thing is to draw an N afterwards, which is saying it could go on for however many monomers we had. So if N was 50 on the left hand side, it will be 50 on the right. Okay, let's zing to the next question. 8.3, polyethylene can be strengthened with wood particles to make a building material. The building material consists of a wood particle reinforcement embedded in a polyethylene matrix. What's the general name for materials like this? Well, this is a bioplastic. You put something living, biology, into a polymer, a plastic. So a biopolymer or bioplastic. Right. 8.4. The amino acid beta alanine has the formula H2NCH2CH2COOH. Beta alanine polymerizes to produce a polypeptide and a small molecule. Name the small molecule produced when beta alanine polymerizes. Well, let's look at the polymerization of beta alanine. Okay, so what I'm doing now is drawing out one molecule of beta alanine in pink or purple, however you visualize that color I'm using. My GCSE art skills are poor. I got a D, which is like a level 3 in GCSE art. My silly mistake. I thought it'd be a DOS subject. That's why I took it. A nice relaxer. But it wasn't. The other beta alanine I've drawn in blue. Now it's these, the H and an OH snap off. What do you think H and OH form? And then they join together, and I'm going to draw the rest of the molecule over here, and they join together to form the polymer. What molecule therefore is removed? What molecule got removed when I snapped off the H and the OH to join them together? You've guessed it, absolutely. The molecule that's removed is water. So the answer here is water. You can write H2O, and this is just joining two of them together. You actually would get, if you make a big polymer, you'll get two water molecules for every two monomers you join together. This is known as condensation polymerization, precisely because water is eliminated in this reaction. Water is removed in an elimination reaction, and we call it condensation because you'd actually see water forming. Okay, cool. Let's move on to the rest of the questions. So we've got 8.5. An amino acid can be represented as H2NCOOH. The relative formula mass MR of this amino acid is 75. Calculate the relative formula mass of this section represented by the grey block. So we just want to do 75, which is the total thing, minus H2NCOOH. So simple maths. We want to take away 14 for the nitrogen, 2 ones for the hydrogen is 2, 12 for the carbon, 16 times 2 for the 2 oxygens, 32, and 1 more for 1 more hydrogen. So 75 minus 14 minus 2 minus 12 minus 32 minus 1, and that all comes to like 61. So our answer here, the relative formula mass for that grey block in the middle, is going to be 14. And that's going to be C with two H's attached, CH2. But they don't ask you for the formula of it, but it would be CH2. Okay, let's zing down. We're nearly at the end of this question. Figure 6 represents part of a naturally occurring polymer molecule produced from glucose. Draw a circle around the repeating unit in the polymer. So can you see that the same molecule is repeated 3 times here? Hopefully you can visualize that. And then look, I'll circle all 3, but you only need to circle 1 to get the mark. See, look, I've circled these 3. You'll notice I'm circling the oxygen on the left and not the one on the right in each one, so they're separate. I could do it the other way round, doesn't really matter, but we've got 3 separate molecules here. Now, what big polymer molecule, what long polymer would you make from lots of glucose? That's why it's saying suggest the identity. And the answer could be starch, it could be glycogen, and they'll probably also accept cellulose in the exam, even though technically that's not correct. It might be all accepted, but starch is your best answer there. Okay, figure 7 represents the structure of a naturally occurring polymer. Hopefully you know the name of this polymer. This is DNA, deoxyribonucleic acid. Give the general name of the 4 different monomers that make up the structure shown. So most people might say ATGC, they're the 4 monomers. They're the 4 bases. Now, each one of those bases is attached to a monomer that joins together to make DNA. And the answer is a nucleotide. A nucleotide is actually made of a circle there, which is a phosphate group, pentagon, which is the deoxyribose, and then I've put an A in a rectangle, which is the base. So you could have an adenine nucleotide, a thymine nucleotide, a guanine nucleotide, or a cytosine nucleotide. Coolio. Name the shape of the... Okay, question 9. This question is about reversible reactions. When 6.8 grams of hydrated copper sulfate changes into anhydrous copper sulfate, 2.99 grams of anhydrous copper sulfate is produced. So we start with 6.8 of hydrated, we end up with 2.99 of anhydrous. 1.47 kilojoules of energy is taken in from the surroundings. Hydrated copper sulfate goes to anhydrous and water. Calculate the maximum mass of water that can be produced from 11.7 grams of hydrated copper sulfate. So if you had 4.68 grams of hydrated copper sulfate, you end up with 2.99 grams of hydrated copper sulfate. How much water would you have? So think about the conservation of mass. Well, we can do 4.68 minus 2.99, and we'll find out exactly how much water that we would have left over. And so we're going to have 1.69 grams of water left over. Now that's going to score you a mark there out of 3 marks. So actually there's a ratio between the copper sulfate and the water of 4.68 to 1.69. Now I want to simplify that ratio. So divide both by the smallest, 1.69 divided by 1.69, 4.68 divided by 1.69. And what we're going to get is 2.7 basically, or 2.77 to 1 is the ratio of hydrated copper sulfate to water. So they say to us, when we have 11.7 grams of hydrated copper sulfate, how much water would we get? Well, if we had 2.77 grams of hydrated copper sulfate, we get 1 gram of water. Now we've got 11, so how much would we get? So we're going to do 11.7 grams of hydrated copper sulfate. And we're going to divide that by 2.77, which is the ratio of hydrated copper sulfate to water, and that will give us how much water we can make. So we've got 11.7 grams divided by 2.77, which is the ratio of copper sulfate to water, and we'll find out exactly how much water you can make if you have 11.7. And you'd be able to make 4.22 grams of water, which is the answer. So that's going to get you 3 marks. There are other ways to work this out. This is the way that I've done it. Okay, moving on to 9.2. 15 grams of anhydrous copper sulfate completely changes into hydrated copper sulfate when water is added. Calculate the energy transferred to the surroundings. We know the energy taken in when 2.99 grams is produced is 1.47. Whether it's produced or released is going to be the same amount, but we know 2.99 grams produces 1.47. So how much does 15 grams produce? It's going to be a lot more, isn't it? It's going to be like 5 times more. So we want to do we know that 2.99, once again, has taken in 1.47. We're looking at how much is released here, the opposite, but it's the same kind of thing. We know, so we're going to do 15 grams divided by 2.99 times 1.47, and that's going to give us the amount of kilojoules that are transferred to the surroundings. The amount of energy in is going to be equal to the amount of energy released when either you make it or you break it, essentially. The answer is 7.37. Okay, going on to 9.3, the equation for the reaction is 2 nitrogen dioxide molecules, gaseous, turn into dinitrogen tetraoxide colorless, N2O4. Of course, dinitrogen tetraoxide, the tetra means 4 oxygens. The forward reaction is exothermic, so it's like a hot reaction on the right-hand side or in the forwards direction. So I like to think of that. I'm going to not do this in blue. Let's do this in red because it makes a little bit more sense. We don't use the words hot and cold in our answers, but it's good to think of it like that. So an exothermic reaction is a hot reaction. Things get hot, the temperature increases. Endothermic is cold. I'm putting it in brackets because you don't want to use hot and cold terminology, but it helps. Okay, and I've written it in red for hot, blue for that. So what happens when the position of the equilibrium in this reaction, if the temperature's increased? Remember Le Chatelier's principle, right? The dude who said, whatever you do to a reversible reaction, it will do the opposite. So if we increase the temperature, the reaction is a reversible one. It tries to do the opposite. So it moves instead from the hot to the cold. You've increased the temperature, it tries to get cold. So we're going to say it shifts to the left. Okay, and you can call this the left and the right or the backwards and forwards. But in this question, they've called it left and right. Right, 9.4, zing a zing zing. Let's go. A teacher seals a brown coloured mixture of nitrogen dioxide and dinitrogen tetraoxide in a gas syringe. Figure 8 shows the sealed gas syringe. Syringe position is here. We've got a seal at the end and a mixture of gases in the end there. The teacher pushes the piston in, increasing the pressure, right? Reducing the volume, increasing the pressure. What colour is the mixture once after the pressure is increased? Well, let's check out this equation. We need to zing, zoom in here. So on the left-hand side, we have 2 gas moles or molecules. How do I know that? There's a big fat 2 in front of the NO2. On the right, there's only 1 gas molecule. Although it has a 2 and a 4 in the equation, there's no big number in front of it, no coefficient. So we've only got 1. So we've got more gas on the left, less on the right. The left side has more gas. So this is the high pressure side. Remember what Le Chatelier said. He said, whatever you do to the reaction, it will do the opposite. So if we increase the pressure, which side does it want to go to? It wants to go to the side with the least pressure, with the lowest amount of gas molecules, and that's the right-hand side. So it's going to shift to the right-hand side. Now, what color? So when we increase the pressure, it's going to shift to the right-hand side because there's less gas molecules on the right, so that lowers the pressure. Remember, it's doing the opposite. We'll rewrite the equation here. 2NO2 goes to N2O4. We've got less gas molecules on the right, so it's going in towards the N2O4. What color was the N2O4? Let's check in the question up here. The N2O4 was colorless. So if you're going to have more N2O4 because the pressure's increased and Le Chatelier says it tries to do the opposite, so it wants to make less gas molecules, so it shifts to the right, you're going to get more colorless stuff produced. And what does that mean? If we force the equilibrium to the right and we get more colorless, we're going to get a lighter shade of brown. There's going to be less NO2 and more N2O4, which is colorless. So the shade is going to get lighter. So the correct answer is the bottom one down here. The mixture is going to be a lighter shade. Now, if we reduced the pressure, then it would do the opposite and go to the side with the most gas molecules, which is the left-hand side, because there's a big 2 there. And that means it would get darker, it would get browner. But we're not doing that in this equation. Remember, Le Chatelier always does the opposite in a reversible reaction to what you change. Hydrogen iodide gas decomposes into hydrogen gas and iodine gas at high temperatures. The equation for the reaction is 2HI goes to H2 plus I2. Explain the effect of increasing the pressure on the equilibrium position. Which side has the most gas molecules? Neither. There's 2 there's 2 G molecules or G moles on either side. You've got big fat 2 in front of the HI, but then we've got H2 and I2. They're 2 separate molecules, so they're also a 2. Even though they don't have a 2 in front of them, there's also 2 Gs on the right and 2 Gs on the left. Same number of gas molecules, gas molecules on either side, which means the pressure is equal each side. So changing the pressure will not favor either side because the pressure is equal. So changing the pressure will not shift the position of equilibrium. And the reason is because there is the same number of gas moles or molecules on each side. Okay. There we go. So the equilibrium position stays the same. So it will have no effect on the equilibrium position because the number of gas moles is equal on both sides. 2 marks. 9.6. Suggest the effect of adding a catalyst on the equilibrium position of this particular reaction. Well, actually, catalysts never affect the equilibrium position of any reaction. They increase the speed of the reaction, so you reach equilibrium faster, but they don't shift it to the left or right. They don't change the position of equilibrium. Right, copper forms colored compounds. This is hydrochloric acid is added to an aqueous solution of copper compound A. The word equation is shown here. The reaction mixture is green with both copper compounds are present in the solution at equilibrium. How can the equilibrium position be shifted to make the reaction mixture more yellow? If we want to make it more yellow, we need to shift the equilibrium to the right. Now, we're not dealing with gases here, so we can't change the pressure. And we haven't been told if this is exothermic or endothermic, so we can't change the temp. But we have been told is that it's using solutions or concentrations. So if we increase the amount of hydrochloric acid, Le Chatelier will say it will do the opposite, remember? He said that, look, it's going to try and do the opposite. So if you make more HCl, hydrochloric acid, we'll try and remove that by shifting it to the right, and forcing the equilibrium to the right will reduce the HCl, which you've just increased. So add more hydrochloric acid, it will shift it to the right, we'll make more of copper compound B, and we'll get a more yellow color. So the clue here is add more hydrochloric acid. Le Chatelier says it will do the opposite. 9.8, the concentrations of the substances in this reaction do not change at dynamic equilibrium. Explain why. So dynamic equilibrium means the reactions are still happening. You're still making product, you're still making reactant, but the forwards and backwards or left and right reactions are happening at equal rates. Okay, so we're making the exact same amount of product as we're making reactant. This means you get the same amount of product forming as at the same time you're getting the same amount of reactant forming. So the same amount of product and reactant are forming per second, or yeah, the rates of reaction are both equal. Um, this means the mass of the products, or the amount of products and the amount of reactants, stays the same. But it does not mean, and this is a big misconception with equilibrium, equilibrium doesn't mean you have the same amount of reactant and product. You have the same amount forming, but you don't have the same amount of both. So imagine at equilibrium, I have 10 on the right and 5 on the left. They're not the same amounts, but they're constantly changing. So one's going from right to left and one's going from left to right. Then I'm still left with 10 and 5 because I'm taking one from the right and adding it to the left, and one from the left and adding it to the right. So the numbers stay the same. The reactions are still ongoing, and I'm making the same amount of product and same amount of reactant, but the actual amounts are different. Okay. Anywho, yeah, so that's a misconception. Do not say the amount of product is equal to the amount of reactants, but you can say the amount of reactant forming and amount of product forming are the same. Easier to just say the rate of reaction of the forward and backwards reaction are equal. Oh, and the amount of product and reactant do not change is the easiest way to say it. Right, so to improve agricultural productivity, Table 4 shows information about 3 compounds, A, B, and C, that can be used as fertilizers. So this is one of those long-ass ones where you've got to use the table and say the benefits. You've got to evaluate and say the benefits of using the different compounds to grow your crops. A scientist analyzed the percentage of nitrogen, phosphorus, and potassium in the soil. The percentage of nitrogen and potassium in the soil are low, so this means the farmer needs potassium and nitrogen. However, they had enough phosphorus. Evaluate the use of these compounds to improve the agricultural productivity of the soil. So this one's quite easy. We've got the cost here, and we've got the amount of potassium, nitrogen, and phosphorus held in compound A, B, and C. Which combination or any of these compounds would you use to improve the soil fertility? We've been told it's low in nitrogen and low in potassium. So if you've been told it's low in nitrogen and potassium, which 2 compounds would you definitely want to add? And which one wouldn't you need to add? So the farmer wouldn't really need to add compound C, the last one. I put a cross next to it up there. Yes, it's high in nitrogen, which the soil needs, but it's the most expensive. It's 0.35 pounds per kilo, 35 quid per kilo. And you're getting a lot of phosphorus there that you don't require. So that's kind of wasteful and would be a bit of a wasteful environmentally, and it would be expensive. So you shouldn't really use compound C. However, the farmer should use compound A and B, and you need to kind of write that down and explain that. Why? Because, well, they're low in potassium, and compound A has 52% potassium, and compound B will give you all the nitrogen you need. Plus, compound A and B are cheaper than compound C. So as long as you take all of those things into account, you're going to smack out the 4 marks. So really, your evaluation and conclusion needs to be use a combination of A and B, because they contain high amounts of potassium and nitrogen. You can't get both with one of them. You can't use A on its own or B on its own. So you need both A and B to get all the nitrogen and potassium that the soil's low in. And they're both cheaper than the compound C. Compound C, yes, you'll get nitrogen from it. There will be some benefit, but you won't get any potassium, and you'll get lots of phosphorus, which is wasteful because the soil doesn't need the phosphorus, the P, 23% P, and it's more expensive. So there we go. So don't use compound C, use A and B. Boom, 4 marks. Lovely jubbly. Let's move on. 10.2, how is potassium chloride, compound A, obtained from the earth? So how do we get KCl from inside the earth? How do we get any minerals out the earth? And you could put mining here, or you could put quarrying, basically digging out the minerals from the rock and then treating them. Name one other compound that could be used instead of potassium chloride, compound A, to give it a similar improvement in agricultural productivity. So they'll accept any potassium compound. I just had potassium hydroxide or carbonate up there, or potassium nitrate. So any potassium compound they'll accept. But the one they're really looking for is potassium sulfate. Okay, they won't accept potassium chloride because that is in the question. Nitric acid is needed to produce ammonium nitrate, compound B. Name a compound to produce nitric acid. Well, to make nitric acid, HNO3, we need ammonia, NH3, and water, H2O. So you could say ammonia or NH3, or you could say water, H2O, and that'd get you the mark. Right, moving on. Phosphate rock contains phosphorus compounds. Plants absorb phosphorus from the compounds dissolved in rainwater. Suggest why phosphate rock cannot be used directly as a fertilizer. And the answer is that it is insoluble. So that would be the reason why you can't use it as a fertilizer, because it doesn't dissolve in water, so you can't spray it on your crops. Okay, phosphate rock can be treated with different acids to produce salts useful as fertilizers. Name the salts which are produced by treating phosphate rock with sulfuric acid and with phosphoric acid. These are right at the end of your CGP revision guide for chemistry, and it's the last part of the chemistry. You just have to know that phosphate rock, if you mix it with sulfuric acid, you make calcium sulfate, or if you mix it with phosphoric acid, you'll make calcium phosphate. They also have another name, each of these. Calcium sulfate is known as single superphosphate, and calcium phosphate is known as triple superphosphate. Anyway, good for revision cards. Like, share, subscribe. Let's get to the marks.
You're still here? It's over.